Physicists have eagerly anticipated a photograph of black holes for a century. These enigmatic phenomena, with their immense power and near invisibility, weigh 2 to 4 times the mass of the Sun. Recent decades of research, highlighted by Michio Kaku's recent announcement, have brought us closer to understanding the intricacies of black holes. In 1916, Albert Einstein's theory of general relativity predicted the existence of black holes, yet it took until the 1960s for the scientific community to find evidence, which came with the discovery of Cygnus X1. This particular black hole, situated in the Cygnus constellation 6,000 light-years from Earth, marked a significant breakthrough, confirming the existence of these celestial entities and fueling a global surge in research efforts. The discovered black hole, Cygnus X1, is approximately 14 times brighter than the Sun and incredibly dense, exhibiting a strong gravitational pull. This force is so potent that even light cannot escape, hence the name black hole. The concept is both fascinating and terrifying, representing a region where gravity is overpowering, trapping everything that ventures too close. Following Cygnus X1's discovery, scientists embarked on a quest for other black holes. Estimates suggest there may be over 100 million black holes in the Milky Way, yet their detection remains challenging. Despite this difficulty, there are likely several million black holes in our galaxy, emphasizing the importance of studying them. The primary concern with black holes is their intense gravitational pull, compressing anything entering them into a singularity. In simpler terms, black holes act as cosmic vacuum cleaners, drawing everything towards them. Research reveals a chilling aspect. If someone were to fall into a black hole, they would be stretched into a single line, a process leading to their demise before the final form sets in. Despite their omnipresence, the closest black hole to Earth is 1,500 light-years away, sparking questions about potential dangers. In 2021, scientists released the first clear photograph of a black hole, specifically the M87 black hole. Capturing several consecutive nights, researchers stitched together individual photos to reveal 3 layers within a black hole, enhancing our understanding of these enigmatic cosmic structures. Black holes are not mere gaping holes of nothingness, contrary to common belief. The structure is complex, comprising 3 layers. The first layer is the event horizon, a point of no return. Once passed, one is inevitably drawn into the black hole. The second layer is the photon sphere, where light orbits, becoming trapped by the gravitational pull. The third layer is the singularity, where everything entering the black hole is compressed to infinite density, and the known laws of physics break down. Adding to the complexity, each black hole is distinct, despite following the 3-layer concept. Studying them directly is impossible, as probes entering the event horizon are pulled to the singularity, facing crushing compression. This challenge forces scientists to study black holes indirectly by observing emitted radiation, gas, and surrounding dust. The inability to explore black holes in 3 dimensions further complicates matters. Additionally, each black hole's uniqueness and the breakdown of known physics inside pose further challenges to comprehensive study. The limitations in observational methods and the inherent complexities make black holes a particularly intricate area of research. The study of black holes poses challenges for traditional scientific inquiry, leading researchers to explore various theories. One compelling theory suggests black holes form from collapsed stars. When a star exhausts its fuel, it can't counteract the gravitational force, causing it to collapse into a singularity. NASA scientists delved into the core of the galaxy M87, discovering a whirlpool of hot hydrogen gas spinning at 1.2 million miles per hour. The stable rotation indicated a colossal mass, estimated at 2 to 3 billion suns, leading to the conclusion of a black hole's presence. Another notable theory involves spinning black holes. In 1963, mathematician Roy Kerr proposed a spinning black hole wouldn't collapse into a point but form a ring or disk called the ergosphere. This rapidly spinning disk challenges the laws of physics. Kerr's solution also predicted the existence of an Einstein-Rosen bridge or wormhole, a theoretical passage connecting different regions or even parallel universes. Falling into a black hole, instead of annihilation, might lead through this tunnel, emerging in a parallel universe through a white hole. These theories contribute to the fascination and mystery surrounding black holes. The concept of wormholes involves understanding the interconnected nature of space and time in Einstein's theory of general relativity. Space and time form a four-dimensional fabric called spacetime. Massive objects warp this fabric, creating gravitational fields that attract other objects. To illustrate this, imagine a sheet of paper representing spacetime. Placing 2 points on the paper and drawing a line between them represents how objects move through spacetime. Now, envision folding the paper in half to create a shortcut between the 2 points. This idea forms the basis of a wormhole, a shortcut through spacetime connecting distant points in an instant. While often associated with science fiction, wormholes are a prediction of general relativity. However, they are inherently unstable and would collapse almost immediately, making direct observation challenging. The existence of an Einstein-Rosen bridge associated with wormholes implies that black holes are not just cosmic vacuum cleaners but could also serve as portals to other regions of spacetime. The intriguing possibility of using wormholes for space and time travel has captured the fascination of physicists for decades. However, even if we could stabilize a wormhole, the theory of special relativity suggests that traveling faster than light, a requirement for practical interstellar travel, is unlikely. Despite the current limitations, the exploration of wormholes and black holes as potential pathways to different parts of the universe or different times remains an exciting and speculative field in physics. The Kerr wormhole, named after mathematician Roy Kerr, is one such intriguing concept, suggesting a theoretical tunnel through spacetime that could connect distant points, universes, or even different times. The Kerr wormhole is a theoretical passage through spacetime, visualized as a ring-shaped portal that could connect different universes or times. However, its feasibility is debated due to concerns about stability and impassability, with critics emphasizing the limitations of Einstein's gravity equations in explaining quantum forces. This controversy underscores the need for a theory of everything that unites gravity and quantum theory. Physicist Michio Kaku has explored this, and superstring theory is a leading candidate. It proposes that subatomic particles are tiny vibrating strings, suggesting a unified framework for understanding the fundamental forces in the universe. Superstring theory, fascinatingly, proposes that as strings move in time, they warp space, giving rise to phenomena like black holes and wormholes while unifying gravity and quantum theory. However, it introduces a complex aspect. The theory requires 10 dimensions of spacetime, a departure from our familiar 3 dimensions of space and 1 dimension of time. To comprehend these extra dimensions, physicists use conceptual models. For instance, consider fish in a 2-dimensional pond, unable to perceive height. Rain causing ripples on the pond allows them to indirectly observe the 3rd dimension. Similarly, although we can't directly see the extra dimensions, the effects on our observed world can be detected. In superstring theory, the vibrations of strings generate energy waves through these extra dimensions, potentially explaining all observed particles and forces, including gravity. The challenge lies in the minuscule size of these dimensions, beyond our direct study. Theoretical models suggest they might be so tightly curled up that they are imperceptible, akin to a rolled-up sheet of paper to an ant walking on its surface. The extra dimensions in superstring theory might be invisibly curled up into tiny loops or spirals, influencing the behavior of vibrating strings. Another suggestion is that these dimensions were more evident during the universe's early moments, gradually collapsing and curling up as the universe expanded and cooled. The mathematical intricacies of superstring theory have led to the exploration of previously untouched areas of mathematics. The challenge of solving the problem of a quantum black hole within this framework has been daunting. Although significant breakthroughs in 2 dimensions have been made, the full resolution in 10 dimensions remains elusive. Edward Witten has referred to superstring theory as 21st century physics that fell accidentally into the 20th century. Recent breakthroughs provide hope that the quantum black hole problem will eventually be solved. However, practical applications like intergalactic travel or time travel, especially concerning black holes, remain distant prospects. In addressing the multitude of questions and potential solutions, Michio Kaku emphasizes the commonality of facing multiple answers in theoretical frameworks like string theory. The quest for the true answers continues, acknowledging the complexity inherent in understanding the mysteries of the universe. Michio Kaku introduces another perspective, challenging the conventional understanding of the Big Bang. He proposes that the Big Bang might not have been an enormous explosion with a deafening noise. The theory lacks an explanation for its cause or mechanism. String theory offers an intriguing alternative, suggesting that our universe could have originated from the collision of two separate universes or emerged from another universe, akin to a birth process. This interconnection between universes is termed a wormhole, akin to a tube linking two bubbles. Kaku suggests that evidence of this cosmic umbilical cord connecting our universe to another might already exist. This perspective raises the possibility that our existence is within a black hole, unbeknownst to us. It adds a layer of complexity to our understanding of the universe, challenging traditional notions of its origin and structure. Think about it. Because we exist in 4 dimensions and can't see anything beyond it, it's possible that we're actually in a black hole, and the black holes we're studying are actually wormholes to these other dimensions. Do you think there could be truth to that theory? Let us know in the comments below. If you like this video, please give it a thumbs up and hit the subscribe button with notification bell ring. And we'll see you in the next one.